Now that we've learned about how vectors look when they're represented in 3 dimensions or in 3 space, I wanted to look at how we handle operations with vectors once we've extended things into that 3rd dimension. So consider these two vectors, A and B. The rules for adding and subtracting two vectors are actually just a very simple extension from the 2-dimensional rules. To add two vectors, I just add their x components together, their y components, and their z components. And to subtract two vectors, I just subtract their x components, y components, and z components. Scalar multiplication is also an extension from the 2nd dimension. When multiplying a vector by a scalar, I just have to multiply all 3 components by that same scalar. The 0 vector also gets a little bit of an upgrade in 3 space. It now has 0 as its x component, y component, and z component. Otherwise, though, all the other rules associated with the 0 vector stay the same. So let's do a quick example with 2 points A and B with the coordinates listed, and we're going to find the vectors AB, the vector OA, and the vector we get from adding AB to OA. So to find a vector between 2 points, we establish that that is done just by taking the coordinates of that 2nd point, the point where the vector ends, and subtracting the corresponding coordinates from the point where the vector starts. So I get that the vector AB is 1, -6, and -3. Vector OA is simply the position vector of that point A. It's saying the vector that goes from the origin to that point. So we know to find that vector, we just take the coordinates of the point, and we use them as the components of the vector. For this final question where I'm adding two vectors together, I'm taking the vector 1, -6, and -3, adding that to 2, 1, 4. And based on the rules we just outlined, that's simply a matter of adding the components together. So I would do 1 plus 2 is 3, -6 plus 1 is -5, and -3 plus 4 is 1. And that's my resultant vector for that addition of two vectors. As our final example in this video, I wanted to actually look at solving equations that involve vectors. So here I give two vectors. A is the vector 2, 1, 2, and B is the vector 3, -5, 4. And I want to solve for the vector x if I know that 2a minus 3x is equal to b. Now, for all intents and purposes, a vector equation like this seems really unfamiliar, and like it would be a very challenging question to have to solve. But this works in very much the same way that any algebraic equation would, except now all of these variables are just represented by vectors instead of scalars. So I can take this vector equation and substitute in the known quantities. So I have 2 times my vector A, which is 2, 1, 2. And I'm subtracting 3 times my vector x. Now I don't know the components of x right now, so I'm just going to call them x1, x2, and x3 for the x component, the y component, the z component. And all of that's equal to 3, -5, 4. That's my vector b. So what I can actually do here is, using scalar multiplication, multiply that number in to each of the components. So I'll multiply the 2 into this vector, and I get the vector 4, 2, 4. I will multiply a 3 into this vector, and I end up with 3x1, 3x2, and 3x3. And now all of that is equal to 3, -5, and 4. And then the great thing about vectors is I can actually break this down by components, because the x components, the y components, and the z components are independent of one another. They don't have any effect on each other. So the value of the x component is not going to change the y or the z. So I can actually deal with them each individually. I can take the x components here, pull them over here to the side as one equation. 4 minus 3 times the x component of my unknown vector is equal to 3. And that allows me to rearrange and solve that equation to figure out that the x component of my missing vector is 1/3. I can do the same thing for the y components to get an equation just from that part of the vectors. And that equation would be 2 minus 3x2 is equal to -5. Again, x2 is going to be completely independent of whatever the value in x1 was, so I can set up this equation and solve to get that the x2 value is 7 over 3. And then finally I'll do the same thing for the z components. My equation is 4 minus 3x3 is equal to 4. And when I solve that, I actually find out that the z component of my vector is 0. So what that means is that my vector x that I was asked to solve for has components 1/3, 7/3, and 0. And so I've found a solution vector to my vector equation. As we continue working in 3 dimensions, we will encounter more vector equations that we can solve, connecting to a whole range of applications. These vector equations can be solved with these basic principles that we looked at here, the notion that the components of a vector are independent of one another, and therefore we can separate them into separate equations to actually go about solving for any unknown values.